All right, everybody. I think all the important people are here. So everybody else, I don't know where they are, but we're all here. I'm glad you guys are here. Hope that you are doing well and having a good week. Super stoked for today, as I always am. I look forward to being here with you guys. We have a lot of announcements to make about what's coming up over the next week. If you've been paying attention, you know there's an exam actually next week on Thursday. So I'm going to talk a bit about that maybe after the break today. I think I'll just make sure we have everybody here before I give a big long overview of that. But I am going to talk about the exam, try to get you a little bit oriented on where we're at and the studying that you might want to start doing for that. So that'll be part of what we need to do today. In terms of the rest of it, we're also going to finish chapter 5. Also during the break today, if you want to ask questions, there's actually 2 sections on the homework that you're currently working on, which are 5.2 and 5.3. We haven't gone over 5.3 yet, so I don't think anybody's gonna have any questions on those problems as of yet. But if you had anything from 5.2, there were some people in my morning class who had gotten a good start on that, and we took some time to look at those. And if you guys have questions on that, we can take those as well. But what I'd like to start with today, though, actually, is just jumping right back in to where we left off on Tuesday, so that we can really finish up chapter 5. It's a really quick chapter, especially because you guys watched that extra credit video. It sort of helped us springboard into this a little bit faster. And so I'd like to kind of finish this chapter up right now, actually. So I just put a little bit of a recap up on the board, nothing too deep. But we're looking at sets of vectors. And again, these could be from any vector space. So these could be, it could be a set of polynomials, it could be a set of matrices, it could be a set of calculus functions, or any other types of vectors that you have. But we're going to now have an inner product defined on this vector space. Okay, and that's what we call an inner product space. And so we can talk about the angles between the vectors in this inner product space. And a 90-degree angle corresponds to vectors that are perpendicular to one another. And I mentioned this definition on Tuesday. The set is an orthogonal set of vectors if the inner product of any 2 of them is 0. Okay, so you just go through, you take any pair of them, match them up 2 at a time, just take 2 of them, and you always get 0 for every inner product. Then those vectors are orthogonal as a set of vectors. And then if in addition, each of the vectors is a unit vector just means the norm is equal to 1. So if the vectors all have a norm of 1, so we have orthogonal vectors that are unit vectors, then it's actually an orthonormal set of vectors. Okay, so we have these 2 concepts. You can't talk about them unless you have an inner product in your universe that you're working in. So with that in mind, I have a little warm-up problem. I thought this might be a nice thing to practice here. Let's show that these 2 vectors consisting of 1 and then the square root of 3 times the quantity 2x minus 1. Let's show that that forms an orthonormal basis for P1 of R. Okay. So actually, before I even answer this question, can somebody tell me if there's anything wrong with this question? Is there something about this question that actually doesn't make sense that I need to fix before we can go on? Dylan?
You want to give it a formula for the inner product?
Exactly. If I want to be able to decide if vectors are orthogonal or not, I have to have an inner product formula for how to test that. And we don't have one. Nothing was given to us in this question. So I'm going to add that right now. So I'm glad that we caught that early. So where I'm going to define the inner product of, let's say, f and g. Okay. And I am going to use, let me just get my formula to be what I want it to be. I'm just going to use the integral from 0 to 1 of f of x times g of x times dx. Okay, so we'll use that as our inner product, okay? This was actually the standard, most common type of inner product to put on functions that was in the video that you watched. But the only thing is, you can use any limits of integration in theory. And two functions that are orthogonal with one set of limits of integration might no longer be orthogonal with a different set of limits of integration, right? So it really is so easy to tweak these inner product formulas and sort of change everything about what's going on. Yeah, so we have to be a little careful with that. Anyway, so I would like to show that this is an orthonormal basis. These two vectors are an orthonormal basis. Incidentally, when I say orthonormal basis, I'm going to add one more little side note here. That just means it's a basis that is also an orthonormal set. Probably what you would have assumed, but this is a basis plus orthonormal set. So I want to know that my vectors are a basis for P1 of R and that they are orthonormal as a set of vectors. Okay, so with all of those clarifications now, with all of those clarifications on the question, I think now I can finally start solving this warm-up problem. Okay, so let's get my blue marker going for the solution here. And let's see what we think. Let's start with just the basis part. So let's forget about the inner product for a minute. And let's go back to chapter 4, where we were studying bases and so on and so on. And can somebody help me understand, these two vectors are supposedly a basis for P1 of R. Can anybody make any relevant observations that would help me understand why they would be a basis? Go ahead.
Is it because it's in the X direction?
Not really. This is not a visual example. These are polynomials, so we don't really have a graphical representation of it necessarily. So if I hand you a set of vectors, I've actually done this already many times. If I hand you a set of vectors, I can ask you, well, first of all, what is the definition of a basis again? Let's just review for our midterm. A basis the set of vectors must be two things. What are they? Li, linearly independent, and a spanning set. Okay, so you've seen me hand you vectors before, and I will ask you, are those vectors Li? Are they a spanning set? Are they both, or are they neither? Right, we've done that. I think we even did some group work on that. So let's just practice that right now. I've got these two vectors here, and if you remember, we can always rule out two of those four wrong answers just by looking at it, right? So what do I want to be thinking about here? Does somebody want to help me with this?
Maybe the dimension of P1?
Oh, the dimension of P1 of R would be super important. Exactly. So what is the dimension of P1 of R?
2.
It's 2, right? Okay. And the other thing that would be important that we could look at right away, just glancing at it, would be what?
Okay.
The number of vectors in my set, right? And I was calling that K earlier, right? And that would just be K. Now remember that when these two numbers match up, then the vectors are both or neither. They're both or neither, right? It can't be one without the other. So this will either be a basis or it will fail both properties. Can somebody tell me why I know just by looking at these two vectors that they will be Li? Go ahead.
Scalar multiple of each other?
They're not scalar multiples of each other. Exactly. I cannot take, so if I look at my set here, guys, I cannot take the first vector and multiply it by a number and get the second vector. If I take 1 and I multiply it by a number, I'm only going to get numbers. I'm not going to get something with an X in it. So also I'm going to note these vectors are Li, since, as Chris pointed out, since they are not scalar multiples. They are not scalar multiples of each other. That's a really good observation. And we can see that just by looking at them. Now, I'm just going to remind you guys, this scalar multiple reasoning, I had a little warning about this. You can only use it when you have exactly two vectors, which is what we have here. We have exactly 2 vectors, but if we had been given 3 vectors or 4 vectors or more, then if we wanted to test the vectors for if they were Li or not, for a larger set, I'd have to lay the vectors into the columns of a matrix, right? And augment it with zeros and do a bunch of EROs. We're not gonna do any of that right now. Okay, but because there's only 2 vectors here, right? Because k is equal to 2, I can just say they're not scalar multiples of each other, therefore they are Li. And if they are Li, then they are also a spanning set because the k matches the dimension of V, right? So since, let me just come up here to finish this, k is equal to the dimension of P1 of R. This now implies we have a basis. All of this, by the way, guys, is just reviewing from chapter 4, really. This implies that we have a basis at this point. Okay, so we've got the basis part. We've got the basis part checked off pretty good. Is everybody okay so far with everything in the blue writing? Okay, this is just explaining that it's a basis. Okay. The next part of it is the orthonormal part. So I have a basis. Now let's go to the new material that we're working on in chapter 5. I would like to know that these vectors are orthonormal. Well, to be orthonormal, I've got it up here for you in the recap. To be orthonormal, all of the vectors have to be unit vectors. And before we even get to that, those vectors have to be orthogonal, right? So I'm going to just check the orthogonal first because that's really a prerequisite. Being orthogonal is a prerequisite to even having a chance to be orthonormal. So let's just check that the 2 vectors that we were given are orthogonal. I'm going to take the inner product of 1 with the square root of 3 times the quantity 2x minus 1. Okay, and to be orthogonal, we need this to be 0. Okay, so this is why I need to have my inner product formula, which is given right here in the question. I'm going to integrate. I'm going to do an integral from 0 to 1 of f of x times g of x. Well, that's just the product of these 2 functions, which is literally just what you see here, the square root of 3 times the quantity 2x minus 1. Nice. Okay, and we can pull out the square root of 3, and then when I anti-differentiate 2x minus 1, I just get x squared minus x. It's pretty easy to do this integral. And so we'll end up with something that evaluates easily to 0. So that does equal 0. When you plug in the limits of integration there, you get 0. And that's what it needs to be the case. You need the inner product of these 2 vectors to be 0. That make sense? So I just pulled the radical 3 out, and I integrated 2x minus 1, which is right here. Evaluate it from the limits of integration, just like you would have done all of your calculus classes. Okay, so once the vectors are orthogonal, now I have to work on the orthonormal part of it, right? I have to make sure that my vectors are orthonormal. Well, that means I have to find the norm of each of my vectors and make sure that it equals 1. So I have to take the norm of 1, for example. Now, actually, before I write down what that is, let me just remind you in general over here, I should have put this in the recap. The norm of a vector is the square root of the inner product of that vector with itself. So this is one that we have to make sure we know. And just because this is a 1, don't assume that it automatically has a norm of 1. We actually need to show it. We actually need to write this out as a square root of the inner product of 1 with itself. Okay, because that's what my vector is. I put it in there, and now underneath this square root, we're going to do an integral. Right, so we're going to now integrate from 0 to 1 of 1 times 1. So 1 times 1 times dx, right? Basically all you have. And to do that integral, of course, is easy. We just integrate dx, we get x from 0 to 1. And that's the square root of 1, which is 1. Okay, good. So that is a unit vector, which is what we were hoping for. Okay, so we got that much down. And then finally, we have to check the norm of our second vector, because all of the vectors have to be unit vectors. So I'm going to do the norm of radical 3 times the quantity 2x minus 1 as well. This is the second vector that we have to work with. And again, this will turn into a square root of the inner product of radical 3 times the quantity 2x minus 1 with radical 3 times the quantity 2x minus 1. So we're just going to use our norm formula for that. And again, we're working underneath this big square root, which gets carried along all the way through everything here. And we're going to turn this into another integral from 0 to 1 of that times that. Actually, the 2 square roots of 3, let me just give myself a little bit of room. The 2 square roots of 3 just turn into 3, and I'll pull it outside because it's a constant. And then I'm just left with integrating 2x minus 1 dx. All I got to do at this point. And, oh, squared, thank you. Yeah, 2x minus 1 squared dx. You've got a couple of options here. You can either just multiply this out underneath this square root, or you can do a quick little u substitution on it. It's kind of up to you. Maybe I'll just practice u substitution. Why not? Haven't done. I don't get to teach that very often, so let me see if I still know how to do it. I'm going to let u equal 2x minus 1, and then the du. The du is just the derivative of that, which would be 2 times dx. All right, so this becomes the square root of 3 times, and then I'm going to have an integral of u squared, and then the dx turns into a du, but it's over 2. So I have a 1/2 out in front, something like that. Am I doing it right? Mm-hmm. You guys have learned this more recently than I have. You probably know it better than I do. So this is the square root of 3 over 2, and then the integral of u squared would be 1/3 of u cubed. But I'm going to rewrite the u as 2x minus 1 again, so that I can evaluate it from 0 to 1 in a minute. So we'll just go back and substitute the original x variable into our result. The 3's cancel here. And when I plug in the upper limit of 1, so I now actually have 1/2 in front. And then this is going to be a 1 cubed. And then minus 1/2 of negative 1 cubed. It's a little messy, but nothing too crazy here. It's actually just 1/2 plus 1/2 underneath that radical. And so it's the square root of 1. And sure enough, that is also equal to 1. It took a little more writing to work that out, but it does come out that way. So steal a little space here. Is everybody okay with that? Any questions on it? It's a lot of just crunching numbers here. There's a lot of crunching numbers. Yeah. So far, so good. So there's quite a bit to this. We had to check that it was a basis. Then we had to check that the vectors were orthogonal. Then we had to check that also the vectors are orthonormal. Now, some of you might be a little skeptical right now about what's going on in this section. Because you're probably thinking to yourself, wait a minute, P1 of R, the easiest basis for P1 of R, wouldn't we just rather use this one? I mean, after all, this is the nicest, this is definitely a basis for P1 of R, pretty much the same reasoning. There's 2 vectors, they're not scalar multiples of each other, so they would form a basis for P1 of R. You might be wondering, well, why in the world would we fumble around with this basis that's got square root of 3 in it, and it's just not as nice somehow, right? Well, actually, these 2 polynomials are not orthogonal if I use that inner product, are they? If I actually use that inner product to calculate this thing, I would just have to do the integral of x dx from 0 to 1, and if I do that, I do not get 0 out of that. So these vectors are not orthogonal. As nice as they are, and they are nice, they're not an orthogonal set of vectors, at least not with respect to this inner product. And maybe I could pick a different inner product where the answer would have come out to be 0. Maybe you could think of some different limits of integration that I could have had instead of 0 to 1. Maybe with some different limits of integration, it would have come out to be 0 as an answer. But at least as I've got it now, this these two vectors are not orthogonal to each other, right? So as somehow I'm making the claim that in some way this is maybe a better basis than that one. Because this one is an orthonormal basis, whereas this one is not, right? You might wonder what is so great about having an orthonormal basis that we would maybe even prefer that. Like, why would we prefer to have these messier vectors here when we could get away with that very easy basis that maybe it wasn't orthonormal, but who cares, right? So here is a little bit of a remark about this, and I'm just going to make this as a passing remark. I don't want to go too far and too deep into this. I'm not really going to have much homework on this or anything, but I just want to make this point that given any vector v in a vector space, okay, we already know that we can write that vector in terms of a basis, right? So we can write v in terms of a basis. Let's say that the basis is the set v1, v2, and ... up to vn. And we know that because a basis is a spanning set. That's part of what a basis is. So because these vectors span the entire vector space, because my basis spans the entire vector space, if I grab some random vector out of V, I know that I will be able to write it in terms of this basis. And we've seen this kind of thing before. We can somehow try to solve it as C1 times V1 plus C2 times V2 plus plus Cn times Vn, right? We know that it is possible to do this. However, we may not have an easy way to come up with what the actual constants are. So the C1, C2, and Cn and so on are to be determined. TBD. TBD, to be determined. So I know that it's going to be possible. I'm that mathematician who wakes up and says, yes, there's a solution to this problem, and goes right back to bed and doesn't solve the problem, right? There is going to be a solution for those constants, but to actually solve for those constants would require us to, set up a matrix, put the vectors in the columns, right? And then augment it with our vector v, and then try to solve for the constants. We could do it. I'm not saying that we can't do it, but it would be some hard work. Except that if your vectors actually form an orthogonal basis, or even better, an orthonormal basis, it turns out that we can get these constants a totally different way without doing a single ERO. And I'm going to show you how. So within this little remark, I'm going to make a little bit of a note here. If we came in here and we took this vector v, and let's just say we dotted it, or we used an inner product on it with one of my basis vectors. Let's say the ith basis vector. So I do this inner product. Now I'm going to go ahead, I'm going to feed in, although I don't know what these constants are yet, I'm going to feed in this linear combination where I have the vector v in my notation. So I'm going to have, C1, V1, C2, V2, comma, Vi, right? And this I is just one of my basis vectors, okay? Now, what you see here in this expression that I've written down is a linear combination that was supposedly equal to V to begin with on the left side. And then over here, I've just grabbed any arbitrary basis vector. But we've learned the axioms of an inner product. Those 4 axioms that I hope everybody's gonna know by next Thursday, right? Basically allows us to manipulate this expression. I could split up plus signs and I can pull constants out. If I do both of those things in one breath, I'm gonna do one quick step here, guys. I'm gonna pull out the C1 and I'm gonna see the inner product of V1 with VI. And then I'm gonna pull out the C2 and I'm gonna make a term that has the inner product of V2 with VI. And we go dot, dot, dot. Somewhere in the middle of this whole thing, I'm gonna have CI, which will be multiplied by the inner product of VI with itself. And then da, 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 we keep going. The last one will be CN times the inner product of VN with VI. So this is just literally expanding the inner product using our axioms. But if this basis was an orthogonal basis, so if the basis is orthogonal, I'm trying to sell you guys on why I want to have an orthogonal basis rather than just any old random basis. What is so great about having this orthogonal basis? Well, if this basis, by this basis, I mean this one. If this basis is orthogonal, then what is the inner product of V1 with VI? Zero, right? It's 0. Exactly. This would be 0. And the inner product with V2 with VI? Also 0, right? There's pretty much all of these terms coming out to be 0, except for this I term right here, which is the only one that sort of survives this orthogonality term that kills off all those other terms. The only thing left here, my friends, the only thing that's left, I'm gonna have to go back up here, have enough room. But the only thing that survives is the CI along with the norm of VI squared. When you take the inner product of VI with itself, you get the square of the norm. So when we think about this box equation over here, guys, for the norm of V, that has a square root on it. So if I get rid of that square root, it causes the norm to get squared, just like I wrote it here. And do you guys see now that actually, so I started with this, and I did equals to this. You see that I can solve for C sub I. C sub I, these are the constants. The C sub i's are to be determined, right? Well, I can now tell you what they are. They are going to be the inner product of V with VI on top and the norm of VI squared on the bottom. So you don't have to put these vectors into a matrix and set up a augmented matrix and solve it. You can actually find your constants numeric. These are just numbers. The numerator is a number, the denominator is a number, and you can just calculate them using your inner product. Okay, so the point here that I'm trying to make is that normally when you take a random vector in a vector space, you're not going to know exactly how to express it as a linear combination of your bases. But when you have an orthogonal basis, then the coefficients of that linear combination are actually just right here. Totally calculable. And actually, if it's an orthonormal basis, it's even better. Then your norms of all of your basis vectors are just 1, and your constants are just these numerators. Yeah, that's actually even better in that case. So this is just a point I'm making. This is a side remark. I'm not going to dwell on it. Why did I even spend any time on it then? It's because I don't like people to not know why we're doing stuff. Like, why do we care if we have an orthonormal basis for a vector space? You wouldn't have a good reason to, why not just take 1 and x as your basis over there? Seems like that would make sense. Well, there's situations where having an orthonormal or even an orthogonal basis can simplify the calculation work that you have to do. You see, that's kind of my point. Anybody convinced? A little bit that you might have a reason to care about this? I hope so, because it's okay. I'm gonna give you a reason to care anyway, because this next thing's gonna be the finding an orthogonal or orthonormal basis is going to be on your exam. That should be enough of a reason, but I'm trying to give you like the real world reason, which is that in the real world, you might like to have a nice way of calculating the coefficients, these C sub i's, in this linear combination, right? That's my point. Okay, but let's talk about how is it that we could come up with an orthogonal or an orthonormal basis. How many hours did Dr. Annan stay up last night coming up with this polynomial? Like, where did this come from? Just out of the sky somehow? No. There's a method that we can use to obtain it. So I'm gonna show you what that is. And that is what is the topic of this next section here, which is actually 5.3 in the book. So we're gonna move into this little section now, and I'm gonna talk about something called the Gram-Schmidt process. It's named after two mathematicians who they both kind of got credit for discovering this. This is a process. What is it used for? For creating an orthogonal set of vectors. That's what it's used for. It's a method for creating an orthogonal set of vectors. So on the exam next week, if you see a problem that says find an orthogonal set of vectors for a basis of P1 of R, for example, you would be using this method to do it, right? So I'm going to explain this method right now. The idea here is, and I'm going to draw a little schematic first, so you might want to give yourself enough room here to kind of draw a little picture. I'm going to draw a little diagram of this so you can kind of visualize how this process works. The schematic that I like to use for this is to sort of start off with any basis for V. So let's say V1, V2, and dot, dot, dot up to Vn. And this would be any basis for the vector space, whatever it is, so for V. Any basis for V right there. Okay, and what we're going to do is we are going to apply a process. By the way, I'm using different notation than what is in the book here. So if you're really following the book closely, it might be worth jotting this part down at least, because I am deviating a little bit here. But we're going to replace this original basis of V1 through Vn with W1 through Wn. And this is going to be an orthogonal basis for V. I'm going to replace the V's with the W's. And in so doing, we will create an orthogonal basis for V. So the process that describes this arrow, this is where the Gram-Schmidt process is actually going to happen. It's going to happen in that process of going from any basis to our orthogonal one. Now, we might decide that that's good enough. We have our orthogonal basis and we're kind of good to go. We'll stop there. But maybe we want to push it a step further and actually obtain an orthonormal basis. So I'm going to extend my little picture here, guys, with another arrow. And I'm going to make another set of vectors, which is going to be my orthonormal basis, U1, U2, and dot, dot, dot up to UN. And this one is going to be an orthonormal basis for V. And this part of the diagram, the part of the diagram over here on the right, I think everybody probably already knows how to deal with. This is where we normalize our vectors. So we do this normalization process to kind of take us along that section of the diagram. Let me just see if we remember how that works. Can somebody tell me if I have, say, the WI vector, how would I make a unit vector? So the orthonormal basis should have unit vectors. How can I make this unit vector out of the corresponding regular vector from the W set?
One.
The norm. 1 over the norm of the W sub I, right? Times W sub I. That's exactly right. You basically just divide in front by the reciprocal of the norm. We did this on Tuesday, right? We did this last time. So you basically take your vector, divide it by its norm, it turns it into a unit vector. That was also in the video that you watched. I kind of showed that process works really nicely. So we kind of already have a pretty good feeling for how to do this piece of the process. Now, just so you know, some of you might be wondering, and I was when I was a student also wondering, could I have started with these vectors and normalized them first, and then orthogonalized them second? It turns out, no, you should not do it that way. Because if you normalize the original set of vectors first, then they still won't be orthogonal. And when you then orthogonalize them later, well, they're not going to be unit vectors anymore. And you'll end up having to normalize again all over. So it is better to do this diagram in this order, which means you're going to first orthogonalize them by this method that I'm about to explain. And then if asked to do so, you can normalize them. Everybody's going to read my questions next week really carefully, I hope. If I ask you for an orthogonal set of vectors, then you don't need to do this whole thing over here. You just take your orthogonal set and you call it good and you move on, right? You don't want to spend extra time normalizing vectors if I'm not asking you to normalize them. So you have to really read, and I'm mentioning that because these words look almost the same. Orthogonal and orthonormal, I've seen people get them mixed up before, just because they look almost the same. So just read really closely. Is he asking for an orthogonal set or an orthonormal set? Okay. Anyway, so I need to explain this Gram-Schmidt process. Is everybody okay with the overview here? This is just like an overview of this section. Okay, if you're good with the overview, now I'm going to actually explain the Gram-Schmidt process. I'll just abbreviate that GS process. Okay. What you need to do is you need to replace the V's with the W's. Okay, and how do you do that? I actually think I probably need more room. Let me just start on our fretboard over here. What you're going to do, guys, is you're going to kind of go through one by one with the vectors from the original set, which would be V1, V2, V3, and so on. And you're just going to kind of normalize them as you go along, as you build this new set. So the W1 formula, what is W1 going to be equal to? How do we get it from the original set? Since it's the first vector and you don't have anything to make it orthogonal with yet, you literally just copy it as V1. So you don't have to actually do anything in terms of orthogonalizing it because it's the only vector that you have. Now, what about W2? I'm going to replace V2 with W2. To show you how that works, again, I could just give you the formula, but I'd like you to understand why and how it comes about. So I'm going to draw on the side over here a little visual for you, okay? And the way my visual is going to look, I'm going to visualize V1 like this and V2 like this. And there is some angle between these vectors. We don't know what it is, but chances are, let's assume it's probably not 90 degrees yet. So these are not yet orthogonal, okay? So what I've done so far is I have declared that V1 is just going to be W1. So we're just going to relabel the first W vector as V1. And I now need to replace V2 with W2. And W2 should be orthogonal to W1. So I'm actually gonna draw the picture of what W2 is first, and then we'll explain how you get the formula for it. W2 is going to be that blue vector that I'm drawing for you right here on this board, and it is supposed to be, if I drew it very well, is supposed to be at a right angle to W1. And you can see that we actually have a little triangle here. There is a red arrow that I'm going to draw right here, guys, on this leg of the triangle. Can you guys all see this red very well? I'm not going to use red very much. I don't like red usually. This is actually called the projection vector. So there's a vector here that you obtain by taking V2. So it's P of V2 along W1. So I write it as P of V2 comma W1. That is called a projection vector. Projection vector. But my main point is, we're actually not going to need to know that projection vector. What we're really just trying to come up with is W2. And I think everybody here would agree, right, that the red vector plus the blue vector gives me the black vector V2, just by vector addition. So if I wanted to solve for W2, I could do this by subtraction. I could take V2 and I could subtract the red vector off of it. So I would be subtracting the projection of V2 along W1. But I want to do better than that. Because I would like to not have to look up what this formula is for the projection vector. So first things first, guys, can somebody tell me how long that red vector would be? Do we have any people in here who've done any trig? I have theta here. Keep in mind, V2 is the vector that's already in your hands. Can I take the length of V2 along with that angle and come up with the length of the red side? What would it be?
Cosine?
Cosine. There's a cosine of theta in here, right? If we just take the length of V2 and let's just go ahead and put this down. So we have V2 here minus, we're going to take the length of V2 times the cosine of theta. However, what I've written on the board as of this moment does not make sense because I cannot take a vector and subtract a number from it. That is like apples and oranges that don't mix. You can't do that kind of an operation. But this is at least how long this vector is. But I need it to be a vector. So you know what I'm going to do? I'm going to take my W1, my big long W1. I'm going to shrink it down to be a unit vector. And then I'm going to stretch it back out by this amount. So I am going to add that to my formula here, guys. Make sure you get this written down. W1 divided by the norm of W1. That's how you make a vector into a unit vector. And then you stretch it back out again to be the exact right length of what that red vector is. That's exactly what you have. Okay, but I'm going to go a little further. Here, guys. V2 minus, we don't want to have theta in our formula, but we have a formula for the cosine of theta, right? So let's just remember what it was. The cosine of theta, wasn't it the inner product of the two vectors, in this case V2 and W1, divided by the norms of the two vectors, which would be V2 and W1. All of that is cosine of theta, and then I have W1 over the norm of W1. So I can just feed in the formula for the angle. This is what we talked about on Tuesday and also in my video that you watched. Cosine of theta is just this expression here. If you're good with this so far, I'm just going to clean it up a little bit now. The norms of V2s can be canceled here. And then I'm just going to rewrite this so it looks a little bit more pretty. So W2, here it comes, guys. W2 is V2 minus, I'm going to make some big scalar here. with W1 outside. And what goes in this fraction is just two numbers. On top, we have the inner product of V2 with W1. And on the bottom, we have the norm of W1 squared. This is W2. So W1 was very easy. It was just equal to V1. And now W2 is this equation here. What it is you're taking V2 and you're subtracting off the part of V2 that points along W1. After you've done that subtraction, you're left with the part of V2 that was absolutely perpendicular to W1. And this now gives you an orthogonal vector to go with W1. Okay, are you guys okay so far?
But
Yeah, Adrian.
so we rewrote the cosine theta
Mhm.
to represent which part of the graph?
It's just this here.
Okay,
And what I'm trying to do is just come up with a formula that doesn't have theta in it. I want my formula to be totally just in terms of the inner product. So I'm getting rid of the theta and writing it in terms of norms and inner products. That's really all that's happening. It's not necessarily represented in the picture
No,
per se.
okay.
The picture is just kind of showing you the big overview strategy.
I see.
So far, so good? Gonna get rid of this. The W3 formula, I won't go through a whole derivation for this one. It's basically a very similar thing. I'm going to write it down though. W3, as you might expect, you would start with V3. And you would start subtracting off the projections of V3 along both W1 and W2. So you'll start with subtracting the inner product of V3 with W1 divided by the norm of W1 squared, all of that times W1, yeah? And then we would also subtract off the inner product of V3 with W2 divided by the norm of W2 squared times W2. Like that. And this would be the formula for W3. Be sure you get your subscripts clear on that. It starts to get kind of messy as you go along with this process. The terms get messier and messier. Okay. So I'm gonna give you guys be a little bit of helpful news here about this, which is, let's clear it off first of all. Couple pieces of helpful information. This, of course, can continue however many vectors you have. Same idea continues. However, I'm going to hereby promise I am never going to ask you to do more than 3 vectors. Several of the homework problems are just 2 vectors, but I will never ask for more than 3. So you don't need to know anything more than this. The other thing is I am going to give you these formulas on your exam. So you don't need to be memorizing these. I'll put them right on the front page. The main thing that you will have to figure out is just when am I supposed to use this process? And the answer to that is whenever they're asking for you to come up with an orthogonal or an orthonormal basis for whatever. And as soon as you see a question like that, you're like, oh, that's Gram-Schmidt. Oh, I've got the formulas already in the front of my exam, and I just have to crunch the numbers away. It's really not that bad. Let's try an example though, just to make sure that everybody kind of understands how this works. So I'll make an example here. Find an orthogonal basis for V equals to the span of -1, 1, 1, 1. Making vector of 4 slots there. And then my second vector is going to be 1, 2, 1, 2. Find an orthogonal basis for V. Now, in this problem, just kind of like the warm-up problem, I also here, at least for now, I have not given you the inner product formula. What are you gonna do in a situation like this if the inner product formula is not given to you in the question? You remember what I said about that?
Dot products for between the two vectors.
Exactly, the dot product. We basically just assume that we're gonna use the standard normal dot product. So unless I give you some funky inner product equation to use, you can just kind of assume that, oh, I must be using the regular dot product, right? So that's fine in this case, because this is a set of vectors in R4. Now, by the way, this vector space is not equal to R4. It is not equal to R4 at all. To have it be equal to R4, you would have had to have 4 vectors that were going to be making up your basis. I've only given you 2, right? By the way, is it clear that, so in my schematic here, the first step is to find any basis for V. Is it clear that these 2 vectors would be able to serve as my basis to begin with? Well, I think they are Li because they are not scalar multiples of each other. Again, it's because there's only 2 of them. I can just use that reasoning. If I hit my head on a rock and I forget that little factoid, I can always take these vectors and lay them into the columns of a matrix, do my EROs, and I'll find out that there's not going to be any free variables. No free variables means Li, right? So these are Li, right? And then why do we know that they're a basis though?
The span.
They're also a spanning set. How do I know that?
The spanning set of V is the spanning set of V.
It's kind of, yeah, so be careful here, guys. We actually do not know the dimension of V. For those of you who are thinking, I'm gonna look at what K, so K equals 2, that would be like, well, dimension of V. Actually, this is a vector space we've never seen before. What is this vector space? This is just all possible linear combinations of these 2 vectors, which is some subspace of R4. But I don't actually know what it is, and so I would be a little bit unsure what its dimension is. So that K versus dimension analysis that I did on the warm-up problem doesn't work so well here. Because we have a vector space that's kind of, you know, out of the sky. Like we have never seen it before. But the reason that these vectors are a basis is that they are not scalar multiples of each other, and because they span whatever they span. Right? This vector space is created as a span of these 2 vectors. So of course, these 2 vectors will span their own span. I'd say that any more emphatically. It's just, it's kind of like it's the very construction of V was done in a manner that made these 2 vectors your spanning set for it. But you don't even have to really think about it very hard. Okay, so they are Li and they span whatever they span, which is what we're looking at right now. So therefore we have a basis. So we have our basis, and I now want to use my Gram-Schmidt process to create my orthogonal basis. So let's get into it then. Let me grab a blue marker and start my solution. And this is going to go really quick. W1 is just equal to V1. And we already know that that's just -1, 1, 1, 1. That's my first vector. I can just write that down immediately. And then my second vector is W2. This one is going to be V2. Let me go ahead and write it down. 1, 2, 1, 2. Minus, and now I have to create some fraction here, times W1. So I'll put W1 there. I'm just using this formula here, guys. I've got my V2 already written down. I've got W1 written down. I just need to fill in this fraction, numerator and denominator of this fraction. In the numerator, I just have to take the inner product of V2 with W1. Let's take a look at that. Here's V2 and here's W1, the inner product of these 2 vectors using a regular dot product. So that's -1 plus 2 plus 1 plus 2. Easy, right? So -1 plus 2 plus 1 plus 2, I think that adds up to 4. That just goes there. Dot product. Regular dot product, nothing crazy. And then in the denominator, I have to put the square of the norm of my vector. Probably lost my norm equation, but just to remind, I'll just put it back up here one more time. The norm of a vector, right? It's the square root of the inner product of v with itself. So I'm just going to square both sides of this to get the norm squared, which just means I'm getting rid of the radical. So I'm just going to take the inner product of W1 with itself. W1 with itself. Just dot this thing with itself. -1 times -1, plus 1 times 1, plus 1 times 1, plus 1 times 1. That actually adds up to 4 as well. So you get a 4 there as well. That's it. And so actually those just cancel, and you end up just getting, for your final answer, you just take 1, 2, 1, 2, and you subtract -1, 1, 1, 1, and you get 2, 1, 0, 1. So I'm just doing some numerical calculations, okay? And so then my orthogonal basis, just to write out the final answer then, my orthogonal basis would be the set of 1, 2, sorry, no. The first vector is -1, 1, 1, 1, and the second vector is 2, 1, 0, 1. By the way, you should be able to check that if you dot these two vectors together, that you do get 0. They're supposed to be orthogonal now. If I asked you if these to make an orthonormal basis, I would now have to go one step further and figure out the norms of each of these vectors and make denominators here. Divide through the normalizing part. So that would be an extra step that we're not being asked to do, at least not on this example. Make sense? One last point I want to make here. What if the person next to you decided to call this vector v1 and this vector v2? After all, it's just a list of vectors. They aren't really in any particular order. So the person next to you could say, oh, I'm going to make this my first vector and this my second vector. Well, then this would have been W1. And W2 would have been based on some combination of subtracting off a multiple of W1. They would have gotten a different answer. They would have had a different answer, but that should not freak us out. We've talked about this a lot, right? There can be many correct answers for a basis for a vector space. So if somebody else decides to lay them out in a different order and do the Gram-Schmidt process from there, sure, they'll get a different answer, but it won't be any better or any worse than your answer, right? It's just a different answer. So it's good to keep that in mind. Okay. Any questions about this so far? Would you like to see one more example? Maybe so. The trouble with this example is it's just with traditional easy vectors with slots in them. What if I now gave you, I think in the homework, there's one that has matrices in it, and there's also one that has polynomials in it. Let's set up at least one more example, and then we'll take a break. Let's just practice one more time. Yeah, so let me start right here with one more chance to practice this. Find an orthogonal basis for V equals the span of, and now I'll make my set. And it's going to be 1 and then x squared and then x to the 4th. So we'll use some polynomials just so we kind of get comfortable with how it would look if we had some vectors that were not just filled with slots. Or we're not just doing dot products, right? Now, as soon as I do something like that, I have to give you the inner product, right? Because this is not Rn anymore. These are polynomials. So I have to give you how to do the inner product. So let's just say where the inner product of f and g. This time I'm going to do integrals from -1 to 1. Okay, so I'm gonna take the integral from -1 to 1 of f of x times g of x times dx. And we're gonna try to find a orthogonal basis for this as well. So I've got three vectors this time, and I can go ahead and label them right away. V1, V2, and V3. And again, they are automatically a spanning set for V because V was created as their span. And it's easy enough to convince yourself that they're also Li. So we'll take that as a basis, and let's just get right into finding these W's now. So I'll go straight into the solution this time, just jump straight in. So we go right to W1. W1 is just V1, and in this case, the first vector was 1. Again, the person next to you could have shuffled these up into a different order, right? And they would have different results coming out, but that would be fine. You can have more than one correct answer to this. Okay, let's go to W2 then, guys. W2 is supposed to be, I've got the formula in the box over here. It should be V2, which is x squared, minus some fraction. Give yourself plenty of vertical room here, guys, to fill in these fractions, make a lot of space for yourself. And then times W1, which is going to end up being 1 here. Each of these parts of this fraction involves doing an integral. Because here's my formula for the inner product. So when I do the inner product of V2 with W1, here's V2 and here's W1. So that inner product is obtained by doing an integral from -1 to 1 of x squared dx. So we do have to put that in there. And for the denominator, we take the norm of W1 squared. So that's just the inner product of W1 with itself. In other words, 1 times 1. So I integrate from -1 to 1 of 1 times dx. All right, let's see if we can just, again, I don't want to dwell on the integrals too badly. When I integrate x squared, I will get 1/3 of x cubed. Just scribble over here for a second. 1/3 of x cubed, and I'm going to be evaluating that from -1 to 1. That's going to be 1/3 minus -1/3, which is actually 2/3. 2/3 on top. And then on the bottom, we're literally just integrating dx. And the antiderivative of dx is just x, which I evaluate from -1 to 1, it just gives me 2. Okay, so just to write that as a nice final answer for W2, it's going to be x squared minus 1/3. Let me know if I'm going too fast. I'm trying to not dwell too much on the integrations, but that's what you should have. And again, you might think, you have such a nice basis here. Why are you replacing x squared with something that's not as nice? X squared minus 1/3. Well, relative to this inner product, these two vectors are orthogonal to each other, right? Which is in some ways an advantage. It is in some ways better than working with the original basis. So that's the idea behind this. Okay, W3, let's see. This one I probably won't work it all the way out. Just going to warn you on that. I'm just going to write out where the terms would go. The W3 is this whole thing over here. So I have to start with V3. The V3 on my problem now is x to the 4th. And then I have to subtract some fraction of W1, which is a 1. And then I have to subtract again, I'll come back to the fractions in a second. I have to subtract some fraction of W2, which was x squared minus 1/3, according to what we've calculated so far. And all of these white spaces that I kind of left here, they're just integrals that come from using this formula, right? So the first one is the inner product of V3 with W1. Okay, so we take V3 is right here, W1 is right here. That's just x to the 4th. So it's just going to be the integral from -1 to 1 of x to the 4th dx. That's it. And then the denominator is just the norm of W1 squared. Again, guys, I'm going to give you this formula. You don't need to memorize it. So I just give you this, take the norm of W1 and square it. That's the integral from -1 to 1 of dx. It's the same as what we had here, actually. Okay. And then on the last term, I have to take the inner product of V3 with W2. So V3 is x to the fourth, W2 is x squared minus a third. So this is going to be an integral. I don't have a lot of room. I'm going to squeeze this in here, guys. X to the fourth times x squared minus 1/3. Sorry, I got a little bit tight on space there. And then the denominator is the norm of W2 squared. That's just going to be the integral of W2 times itself. So x squared minus 1/3 quantity squared. I think a better use of our time would be for me to just leave it like this. You guys could obviously do all those integrals. There's nothing too hard about any of those. And come up with numbers and check it. If you are really interested, I can tell you what I got when I solved it, and you can try it on your own time if you want to. But I trust everybody could do this. The final answer should be x to the fourth minus 6/7 of x squared, and then minus 8/15. It gets a little messy, but there's nothing difficult about it. But anyway, that's what I came up with. So your final basis would be this guy, along with this guy, along with this guy. Right. You notice that you have only even powers of x in everything here. After all, that's what you started with. When you're doing the Gram-Schmidt process, you're really just doing linear combinations of stuff you already started with. Right? You see the W3 has V3, W1, and W2 in it. W1 and W2, well, those were both in terms of the V's as well. So if I only start off with even powers of x, then I'm not surprised that by the time I write down all of my W's, I have only even powers of x in those expressions. At least that's reasonable to expect. Questions? It's super plug and chug. That's what this is. There's not a lot of heavy thinking here. It's just got to kind of use these formulas and run with them, and just be careful with it. Guys, let's take a break. Give you guys a chance to stretch your legs. And if you have any problems on the homework that you'd like me to look at after the break, write them on that sideboard for me. And we'll talk about the exam when we come back in 10 minutes.
See you. Like 6:30. Yeah, you know, you're yeah, like you can be a messy up right now. That's not the exam numbers. One of my options. That's okay. That's not fair. Yeah. So, like this. Oh, patient zero. Wow. I'm trying to send you the.
Oh, yeah. I went, I was started running so bad. I'm like, all right, that's why I like left a little bit, but we'll be fine. I'll be okay.
Where'd you get a nice?
6th floor, grad room.
Oh, nice.
That's where I left my water at. Oh, wait, element is up there.
I just feel from 12 that's not due. You can take away the submit button.
To go to submit button.
Yeah, you do. For homework 12.
Oh, yeah, I saw that.
Do you want the button back again?
No, 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 no.
Okay.
It's okay.
You're happy to not have to worry about that one? That sounds good.
Yeah.
For sure, for sure.
You're writing. It was a long day.
Dude, you're good. Your writing's like way nicer than mine.
No.
I'm tired of writing. All I do is write. Like I have a blister on my middle finger.
Oh, I used to write with middle.
Yeah, look.
You write hard with your pencils?
Yeah, I even have a blister like right here too.
Oh,
I go ham like. I feel bad for my like middle finger, and my thumb, like all blistered up. Like I'm actually really tired of it. I'm over it.
What if you try writing left? Like.
No, I mean I try, but I don't know what's wrong with me. I'm like, I go ham.
Yeah, for my writing is like gray in the back. On an iPad, I can't be writing it.
Yeah, I notice I write so hard when I use lead pencils, like they break sometimes. Especially if they're like
Well,
the 0.5.
oh
The
yeah.
0.5 they break so easily. So that's why I've been using the 0.7. I don't know why I just write so hard. Dude, my favorite pen.
Oh, 5?
No, no, no.
Oh, okay. No way.
It's so beautiful.
I bet it's so fine, huh?
Write it. Write it. Give me your autograph.
Oh, you don't know autograph.
Yeah, give me your autograph. Sign my book.
With determined.
See how beautiful that is?
So sweet.
Dude, the point 338s. I don't like fives. I mean, I have fives because I bought them.
Dude, the ones are crazy, bro. You ever see the ones?
No, I've never seen the
Like a,
one.
it's like a regular marker.
Oh, ew.
Yeah,
Yeah.
yeah.
You don't want to touch that. Yeah,
Yeah.
okay, we'll put tape like right here. I'm sorry. It's okay. Down. It's up with the term.
I said
No, it's
up.
down. No, you said down.
No, I said. No, I wrote.
Oh, yeah.
Oh, you're crazy.
I'm gaslighting you.
The opposite down.
It's like to us, what it is for me to do.
Oh, got you on the spot.
All right, guys, I think it's been about enough of a break. Most folks are back, there's a couple people still outside. Just want to, before we do any more math, I'm just gonna take a quick little pause to talk about the exam that is coming up next week on Thursday. So that is gonna be a week from right now. We have our second midterm. And what is it going to cover? Well, all of chapter 4, except for the one section that we skipped. I see lots of people
Right.
taking pictures with their phones. That is totally good with me. And so that's a lot of material. I think that'll be at least half of the exam would be just chapter 4. It's a big chunk right there. Chapter 5, which we've just finished, basically is a much shorter chapter. It might be roughly 30%. And then we still have one more section to do, which is 6.1. And so I need to cover that. I'm going to start on it in just a couple of minutes. And then we'll talk more about 6. We'll probably be talking about 6.1 the entire time on Tuesday, with the exception of maybe a little bit of group work, because I think I still owe you a couple of group works too. So yeah, and speaking of which, if you're wanting to break it down according to homeworks or group works, homeworks 9 through 14 are the ones that are relevant for this exam. And group works 6, 7, 8, and 9. We've only done 6 and 7 so far, but on Tuesday, we're gonna do 8 and 9. So then we'll do 2 more group works, and that'll be good practice. It'll be good review for the exam to do that. Speaking of those homeworks, homework number 13 is due tomorrow night. So that's due on Friday. And then homework number 14, which is the one that is about 6.1, is going to be due on Tuesday. However, what is probably going to end up happening is on Tuesday, as part of our studying and reviewing, I'm probably going to do quite a bit of homework 14 in class with you. So don't spend the whole weekend trying to do that homework. You can maybe look at a little bit of it, but for the most part, you might just feel like you'd rather do some more general studying instead, and that would be fine. But anyway, so these 2 homeworks we still need to get on top of. Couple of other things, I'm gonna have a lot of office hours. I forgot to write down, I will have hours today as well. So after my last class, I get downstairs about 5:30. I'll be there all evening. So if anybody wants to get a jump on anything, you can certainly do that. But I'm also gonna be around tomorrow evening. I have a meeting, it's gonna keep me around pretty late Friday afternoon. So I'm just gonna push myself right into the evening. Saturday afternoon, I also have a meeting on Saturday until about lunchtime. So in the afternoon, after my meeting, I'm gonna be in my office. And then both Sunday and Monday nights, I will be around. So you can come on in. I am planning to go hiking on Sunday afternoon, so you won't catch me until the evening on Sunday. Monday, I'll probably be around even a little bit earlier in the day. The thing I'm gonna do here that's different than I did for the first exam is, because I just really want to get the scores up a little bit more. I think I'm not the only one who feels that way. We'd like to do a little bit better. I am actually going to do some in-person review sessions. So these are optional. You don't have to come. I am going to record them, and they will be basically the same. So if somebody asked me, oh, should I come to both of them? you can come to both of them, but I'll be doing basically the same problems. Sometimes people like to come one time and write it all down, and then come again and listen to it. Whatever you want to do, and it depends on what kind of time you have. You may not be available for these. I'm going to record these reviews and send them out to you. So if you don't want to come or you can't come but you'd like to know what was being reviewed, you'll be able to do that on Sunday evening. You'll probably get an email from me with the video from the Sunday afternoon review session. So feel free, it's totally optional. But I'm gonna do that as a little extra help. I won't feel bad if you don't come. I don't treat that as, any indication whether you're serious or not about the class. I understand it's the weekend, people have stuff to do. If you can't make it, it's totally okay. If 3 people show up here and I'm talking to, sometimes I come in here, I talk to myself. I love the math so much, I'm still happy. So no matter how many people or how few people are here, I'm gonna be here to do these 2 review sessions. I should also remind you that in Canvas, there's a bunch of stuff. So I've pulled up the page here, guys. There is a file folder that is called Midterm 2 Resources. It's right here. I'm gonna just open it for a second. And again, I'm gonna say the same thing to you that I said before the first exam, which is I don't expect anybody to do all of this stuff. There's a bunch of things here. Just like with the first exam, there are 2 samples. And if there's one thing I could say about the first exam, I do think the first exam was actually not that far off from kind of what the samples look like. I would recommend everybody to do at least one of these. And probably for most of you, it wouldn't hurt to do them both. I do one of them, then take a break and figure out where your weak points are, kind of do some studying based off of that, maybe go back. If you figure out what your weak points are, you can go back to the homeworks or the group works or anything else in this packet and try to shore up any soft spots that you've got, and then try the other sample test. So you've got a couple of those to work with along with the solutions. They're all typed up here for you. That review session I just talked about, again, if you don't want to come, no worries. I got the problems right here that I'm going to be going over, and then the solutions to those problems, I did type those out as well. So you can just do it that way. I just think some people learn better by listening than just by reading something quietly to themselves. So that's why I like to do the review session, just to give an alternative way of kind of soaking it up, so to speak. There's this review packet as well. I won't open it right now, but it has all this information on it, of course, along with sort of a bullet point list of things to be able to do. I would recommend taking a quick scan through that, make sure there's nothing on that list that you're like, whoa, I have no idea how to do that. And if there is something like that, that's a good time to make a note of it and then work on getting that cleared up a little bit, okay? And the review packet even has some practice problems in it as well, even more with solutions that are also here. So everything that's in here has solutions with it, but that doesn't mean you can't come ask me to go over it with you. If you figure out what some of your weaker points are that you want to really work on, you can come to my office and say, hey, I just don't seem to get the Gram-Schmidt process, or I just don't know how to tell if something's a basis or not, or I can't find linear dependencies very well. Whatever it is for you, that's kind of something that you're kind of stuck on, feel free to just drop by. I have a lot of office hours. I want everybody to do well. This is really the reason that I am here in Fullerton, right? I love talking about this stuff. So if you've got questions, I hope you'll take me up on it. You can come, by the way, and Zoom to any of these office hours as well. So if it's not convenient to be in person, that's also okay. All right. So that's next Thursday. I would say the thing that is a little trickier here is I need to cover this 6-point plan, but I'll get it done. I'll find a way. I'll make sure it gets done. Any questions though? Yes. Oh, the extra credit quiz. Thank you for reminding me. Yes, there will be an extra credit quiz. I will probably not send that out until around Monday or Tuesday though. But yeah, I will be giving you a chance to practice. It'll probably be worth like 3 points again towards your midterm. So yeah, thank you for reminding me. Yeah, that will be coming. That will be coming. Okay. Anything else? Okay, anyway, I just wanted to get all that up there for you. Let's take a minute. There were a couple problems from the homework that's due tomorrow night, which is number 13, that people have already started working on, and I've put them on the board right here. And I'd like to just briefly talk about these. I put number 15 up here at the top. Now, I'm actually not gonna do this whole problem right now, but I will at least get you oriented on it. It reads a little bit scary when you look at it. It talks about Legendre polynomials, which are solutions to the Legendre differential equation and blah, blah, blah. So these are apparently very important polynomials. And that's really all that the note is saying here. It's not part of what you have to do. What you have to do on problem 15, guys, is just verify that these functions are orthogonal and then normalize them. So we've definitely done this kind of thing before, so I'm going to take the inner product of F1 with F2 and make sure that it's equal to 0. And then the inner product of F1 with F3, I have to make sure that that is 0. And then the inner product of F2 with F3, I have to make sure that that is 0. So I have to check all of these things. And in case you're wondering what is the inner product that you're supposed to be using, what is the formula for it? Well, this is the vector space of calculus functions from -1 to 1. And so that is supposed to be your clue that the inner product is the integral from -1 to 1 of f of x, g of x, dx. If this had been on an exam, I would have just written that formula there for you. But in this case, it's coming from the book, and so you can find this general formula in the book. Okay, so that's what you need to use, and it's just 3 integrals. Okay, you're just doing these 3 integrals and just checking that they come out to 0. There is a follow-up though. It says use these functions to construct an orthonormal set. So you not only need to make sure that they're all mutually orthogonal, you then need to find the norms of each of these vectors, which is 3 more integrals. You need to find all of those norms and then divide through by the reciprocal of those norms. Yeah, that's how you normalize a set of vectors. Okay, so they're already going to be orthogonal. It's just going to be a matter of normalizing them. So I don't want to take the time right here to do those. If anybody needs to, you can check with me. It's also an odd numbered problem. So there is answers in the back of the book for that, and you can just make sure that you're coming up with the same thing. Okay. So that's number 15. The sort of the skeleton of how you do that problem. Number 7 is a little bit more interesting one. On number 7, also from 5.2, they give you one vector in R3. And they ask you to build it out to an entire orthogonal basis for R3. So they want you to keep this vector specifically, -3, 6, 1. They want you to keep that vector, and they want you to add, how many more vectors would we need to add to end up getting a basis for R3? 2 more vectors, right? Because we know that the dimension of R3 is 3. So here's one of the 3 vectors. We need to add 2 more vectors to this that will become a basis for R3, but it needs to be orthogonal vectors. So, well, I have one idea right now, which is you can call this V1. And then just make any other 2 vectors, V2 and V3, just pull them out of the sky. And then use the Gram-Schmidt process that we just learned. Because the Gram-Schmidt process is a technique for orthogonalizing a set of vectors. Yeah. You notice I'm not writing anything down because it's not the way I'm going to do the problem. This is in 5.2. That precedes when the Gram-Schmidt process was discussed. So you wouldn't have been thinking of doing this problem using the Gram-Schmidt process because the Gram-Schmidt process is in the next section. But just so you know, we could use that method right now. I could just make up 2 more vectors at random, willy-nilly, whatever I want, and then take the 3 vectors and Gram-Schmidt the heck out of them to get my orthogonal basis. Okay. However, there's a way to do this without the Gram-Schmidt process that's maybe a little more elementary, and that would be, so let me give you a little help with this. We don't know what this second vector should be that we're going to add to the basis so far. So let's just keep it kind of generic as like an ABC. And so I'm only working on the second vector. Ultimately, we'll need 3 of them, but this could be the second vector. The point being then that if I calculate the dot product of these 2, I should get 0. I need to get 0 if I want to have an orthogonal basis. So when I do the dot product here, I'm just going to get negative 3a plus 6b plus c, and I'm going to set that equal to 0. Now, that makes a nice little equation for me here. And can anybody, of course, this equation has millions of solutions that work, but let's just write down one that would work. Does somebody want to give me some numbers for A, B, and C that would work in this little equation here? Just kind of eyeballing it. Go ahead, Arlene.
Yeah, 2, 1, 0.
Yeah, we could just try 2, 1, and 0. That'd be 1. There'd be many other correct choices, but I could do that. So you can check. If I dot V with W, I will get 0. I will get 0 out of that. So this could be our second vector. This could be our second vector. But we still need one more because we have to have 3 vectors to have our basis for R3, right? So to get a third one, anybody have an idea? I'll show you the hard way and then I'll show you the really easy way. So don't write down the hard way. You're not going to want the hard way. The hard way is to just come along and say, all right, let's just play that same game again. Let's make 3 more random letters and let's dot this DEF with both of these 2 vectors. So when I dot it with the first one, I get negative 3D plus 6E plus F equals 0. And when I dot it with the second vector, which was 2, 1, 0, I'll get 2D plus E equals 0. And again, I could just hand this to you and ask you to solve for D, E, and F. Now you've actually got 2 equations to deal with. So you might even think that you'd want to put it into a matrix and do EROs and solve it out that way. That'll work. That will work. It's just going to take a little bit of extra effort. But you can find a D, an E, and an F that would work in this. I'm sure everybody in this room, even if you hadn't taken 250B yet, you could probably solve for some numbers for D, E, and F that would work. Okay. But there's an even faster way to get a third vector here that I think is really cool, but it does involve something I've never talked about in this class. But I know that you know it because I know that you've taken calculus. Does anybody know a way, if you have 2 vectors, does anybody know a way of making a third vector that is perpendicular to both of the first 2? Quentin? The cross product of those vectors. I know I have not talked about it in this class, but yes, when you take the cross product of 2 vectors, you create a resulting vector that is orthogonal to both of those 2 vectors. So for the answer here, guys, you can take V, you can take W, and then you can take V cross W as your third vector. If you don't remember the cross product, I will make that an assignment to go onto YouTube and search for cross product of vectors. And I promise you will get a million hits with refresher videos all over the place. It's like very, very common. So yeah, that's a nice way to do that problem. It's a little bit using a little something outside of this class, but I think that's okay. It's okay to remember the cross product of 2 vectors. That's a good concept. Okay. Questions there? I think I'll leave it at that for now on the homework. What I'd like to do, we've got about 15-ish minutes or so. I want to at least get a start on section 6.1. I think I'll do it over here. Chapter 6, specifically 6.1, which will be part of what I'm asking you to study for next Thursday's test. 6.1 is on a subject called linear transformations. Linear transformations. So, guys, when I think about what math really is as a subject, like if somebody said, what is math all about? Just on a very broad level, what would be encompassed in that? I think you get a lot of people, if you polled 1 million people about what is math about, you'd get a lot of people who would say that it is the study of functions. Functions. You have inputs and you have outputs. You're studying relationships between things. And we, in this class, have not really been doing that up until now. Every single problem we do, we're working in one vector space. Here it was calculus functions. Here it was R3. We go from one example to the next, and what you've probably noticed, guys, is that I'm only ever looking at one vector space at a time. We do a problem on polynomials, and then we drop that, and we will do a problem on matrices, and then we drop that, and we do a problem on physics vectors, and it's like they're not really connected to each other. Whereas really a mathematician would want to find relationships between these different, universes that we've been studying. And that is exactly what a linear transformation tries to do. It is, in fact, a function from one vector space to another. Let's actually put the definition right at the top of our notes here for this section, and then we'll dive into this idea more carefully. So, given vector spaces V and W. So I would be usually using V and W to kind of denote my vector spaces here. A linear transformation, which is what I want to define right now. A linear transformation. A linear transformation is a function. It is first and foremost a function. And because the word t is in transformation, you will usually see in the book and in my notes, I'm going to use a capital T for my function. And we always have, when you have functions, guys, you always have inputs and outputs. I'm going to call them V and W. I'm going to use a little arrow to kind of point between these two vector spaces. So the inputs are kind of coming from V. The outputs would be coming in W. And so you might be inputting a polynomial and outputting a matrix. Or you might be inputting a calculus function and outputting some vector. So now we're not just looking at one vector space. We have two vector spaces, V and W. Now they could be the same. There's nothing that says they can't be the same. But we're talking here about the potential to have two completely different universes on the two sides of this transformation. So plugging in objects from one universe and getting outputs that are coming out in some totally different universe. I'm going to write down some examples in a minute, but there is a little bit more to this definition because we're not just going to be talking about functions from V to W. Those functions have to be nice enough that they respect the vector space operations. So both of these vector spaces have an addition and a scalar multiplication. Those are our two main operations in a vector space. And these linear transformations have to respect that. So let's add a little more text here, guys. So this is going to say such that, and then there's two things, right? The first one is T respects addition. T should respect addition. So the way that looks when I write it as a formula is that if I were to take T of the quantity of, let's say, V1 plus V2, if I wanted to add two vectors together and then plug that result into T, it should give me the same thing, guys, as if I transformed the vectors separately first and then added the results together. So T respects addition. Notice that this plus sign is happening within V. But this plus sign is actually on the W side of the equation, right? The outputs. This is an output plus an output. So this plus sign is in here we might be adding two matrices together, whereas over here we might have been adding two polynomials together. Those plus signs obviously are adopted within whichever vector space you're working in, okay? And then there's also going to be something for scalar multiplication. Let's add that to our notes here. T will also respect the scalar multiplication. That's our other vector space operation. And how does that look when I write it out? Well, I usually like to use K for my scalar. So I'll write T of K scalar multiplied onto V1. And for T to respect that, we have to be able to pull the K all the way out of the whole thing. So K times T of V1. Okay, so these are the two equations. And let me just add over here on this side, this is going to be for all vectors. So V1 and V2 are in V, and the scalar K is an element of the real numbers. So for all possible inputs, V1 and V2, this should be true. Okay, that gives us a starting point. Everybody making sense so far? I got to do some examples, but hopefully at least what I wrote there is reasonable. So we don't just want any old random functions off of the street. These need to be functions that actually respect the vector space operations. That makes them linear transformations as opposed to just random functions. And if you have linear transformations, you will be able to take great advantage of all of the linear algebra that we've been doing up until this point. There's going to be lots of basis and dimension and all that good stuff's going to be showing up in this theory. Probably not today, but it's gonna show up in chapter 6. So it's not going away, guys. Let's do. I've got time to do a couple of examples. I think let's try and write a couple of these down. So let's do this one, guys. Let's define T to go from M2 of R to R via, and now I'm going to make the formula here that I'm going to use. So I'm going to input a 2x2 matrix. So just to be clear, this is my V, and then my W is really just the real numbers, which is just one-dimensional vector space. My output, so my input was a 2x2 matrix. My output needs to be just a single real number, and I'm going to spit out A plus 5B. And the question I'm going to ask here about this example is I'm going to ask, is T linear? Now, when I say it like that, that's just my shorthand of saying, is T a linear transformation? So when you hear me asking, is T linear, I just mean it doesn't respect addition and scalar multiplication. This is the idea. So let's try and solve this problem. Let's try to write up the solution here. And guys, I'd really like you to format the solution the way I'm going to do it right now. So try to take some fairly focused notes on this one, just so we get it written down carefully. I'm going to start with the T respecting addition piece of it. This tends to feel, by the way, this starts to feel after a while sort of similar to checking that you have a subspace. You have to check closure under addition and then closure under scalar multiplication. This is also sort of a two-phase verification, one of them for addition and one of them for scalar multiplication. So you'll kind of notice that. Now, what I'm gonna do is I'm going to check that it respects addition, which means I'm looking at this. And on the left side, I have to take two vectors and add them together. In this case, that would be two 2x2 matrices. So T of, let's put the matrix A, B, C, D here, and I'm going to add that to another matrix, which I'm going to use X, Y, Z, and W. You can use whatever letters you want. Of course, I'm just picking 8 out of the letters of the alphabet to make my two matrices, but it doesn't actually matter that much. And my goal is to see if I can split them apart. Right, that equation over there on the right-hand side, I want to have T of the first one plus T of the second one. So I don't want to write that down yet. That's where I'm ultimately hoping to end up at the bottom of this board. But what I've got to do is manipulate this expression to get there. Based on how the parentheses are laid out here, if I ask you what the first thing to do is, would you tell me that the first thing to do is to add the two matrices together? Or would you tell me that the first thing to do is to actually do the transformation?
Do the transformation. I'm gonna add the matrix.
The parentheses are kind of putting everything inside this thing together, right? Actually, let me say it to you another way. My T formula only knows how to evaluate one matrix. So before I can actually evaluate T of something, I have to have just one matrix in my hands. And I can do that by adding the two matrices together. So that is actually the first step. So I just combine these matrices slot by slot. I'm adding the entries together. Exactly like so. Okay, now I am going to be manipulating only, this is something I want on the formatting side of it. Guys, do not be writing anything over here below this first step. The entire verification should happen over here into a single column of statements. And I'm just going to work on the right-hand side. I have a single matrix here, guys, and I'm supposed to transform it. I am now supposed to transform this matrix, and I know how to do it because they told me how to do it right here. I take whatever is in the upper left corner and I add that to 5 times whatever is in the bottom right corner. So what is that going to look like for this matrix? Upper left corner is A plus X. And then the bottom right corner, we have 5 times D plus W. In this step, we lost the T because we actually did the transformation. And we went from the matrix perspective to the real numbers perspective. This is just a single number right here, folks, just a single number right there. Now, does anybody think they might have an idea what I might want to do with this expression to kind of push the argument forward a little bit further?
Simplify.
Yeah, I need to simplify it, but how? Let's keep in mind, I ultimately, can you guys all see this? I ultimately am hoping to get this. This is what should be at the bottom of my board if I finish this thing out correctly. I should get T of the first matrix plus T of the second matrix. It actually is okay to do this. You can kind of work backwards a little bit if you need to. If you kind of get somewhere in the middle of this calculation and you're like, I don't really know what I want to do next with this.
Multiply the 5 with an EW and separate the 5 times 8 plus X plus 5.
Yeah, so the point is the ABCD stuff needs to be in the front. So let's just grab the parts of this expression that involve A, B, C, and D and put them in the front. And then let's grab the X, Y, Z, W stuff and put it in the back. So I regroup the terms so that all of the stuff that goes with the first matrix is in the front and all of the stuff with the second matrix is in the back. This is something that with practice you get kind of the hang of it, how it's supposed to go. And then this becomes that, and this becomes that. And we can put a little check mark there. Now, guys, don't tempt me. Don't tempt me with my red pen. Be sure to include equal signs. Let's write very good notes on this to make sure that it really reads really clearly. So that would be the way to write that one up. Okay, now I'm not done yet because I have to also check that T respects scalar multiplication. So I'll just write it as T respects, and I'll just put a little dot here. And so I'm almost out of time. I'm going to do this one fairly quickly. We'll practice more of these, obviously going forward, but this is just the first warm-up example. For the scalar multiplication, I have my K. So K is my scalar right here. And I only need one of my matrices, which is this one. And what I need to do is I ultimately want to get the K out in front. Guys, I see people messing this one up a lot. They want to just put the K right outside immediately. This K, because ultimately it's out in front, but you can't put it out in front yet. In fact, the first thing you have to do is actually multiply it into your entire matrix. So Ka, Kb, Kc, and Kd. That is a single matrix that I can now use my given formula for. The given formula tells me take the upper left corner and add 5 times the lower right corner. So I just put that down. And when you see this, what's your knee-jerk reaction with this thing here to do? Factor out the K, I agree. If I factor out the K, I get the A plus 5D right there. And lo and behold, that's exactly T of ABCD again. So I can go back and write it as T of ABCD. Notice that I've kept white space over here. I'm not writing in this area at all. It's all happening on the right-hand side. And because both of those things checked out, we can put a yes right here. Okay? Guys, I am going to send you, you don't have to watch the video, but I am going to send you one for those of you who don't want to wait until Tuesday to hear the rest of this story. I will send you a little video that has a few more examples of this so that you don't have to wait. But it will be optional. You can watch it or not watch it, whichever way you want to go. But that's all I've got. Is everybody comfortable with this solution here? Not too bad? Okay, great. I will look forward to seeing you in my office hours, in the review session, or at the very latest next Tuesday for class. Thanks for now. Bye for now.
Thank you, Dr. Adams.